Hello again. This is your friendly heavy physics teacher. And I'm here with a lesson for my Regents Physics class. This is U11 lesson 2, and this is on wave interference. And wave interference is about what happens when waves, more than one wave, moves through the same place in the same medium at the same time. Okay? So just a moment here. Alrighty. Here's the big thing. Here is where waves suddenly depart from the classical way we think about interactions. Okay? Imagine, if you will, that I've got a billiard table in front of me. Okay? And over here, I've got a hopper full of green billiard balls. And over here, I have a hopper full of red billiard balls. Okay? I've got a mechanism that releases those balls simultaneously onto the billiard table. And we have, a chute that come down and they shoot out, and we aim them at a point in the center of the billiard table. So I got green balls rolling this way, I've got red balls rolling this way, and they meet. Okay? Now, according to Newtonian, classical, mechanical ways of thinking about things, what's going to happen to those billiard balls as they meet? Well, boink, they're solid objects. And so what are they going to do? The green ones are going to hit and bounce and go this way. The red ones are going to hit and bounce and go that way. And so if I had a collection hopper over there, it would collect all the green balls. If I had a collection hopper over there, it would collect all the red balls. Never would we expect, would we want to have happen, that a situation where they're coming out and they're colliding and the green ball ends up going over that way. It would not happen. According to classical mechanics, would not happen. Okay? But the same scientists that knew that that would not happen with streams of billiard balls knew that if I took a green colored light and I shined it this way, let's say I had a flashlight or a laser beam, and I shined it this way, okay? And I had a red light and I shined it that way. They meet, they cross over, and what do you expect to have happen over here? If we were to put a screen up, what color of light would I see over here? Now, if this were Star Wars, bounce, and you see green light over here. It's not Star Wars. This is real life. Sorry, it's real life. George Lucas, while lightsabers are cool, no, okay? If the green light were moving this way, the green light continues to move that way, and the screen over here would show green light. If the red light were moving this way, the red light would continue to move that way. At this place in the middle, it would create an interference. It would create a moment where the green light and red light pass through each other. And yeah, they would do something to each other. And if we were far enough away, our eyes actually perceive that moment of interference as yellow. Okay? And we would also perceive that as being brighter than either the green light alone or the red light alone. All right? And so that's what we mean by interference. It's another reason we say that waves depart classically from the behavior of matter. All right? So the waves pass through each other when they do that. That's the essence of wave interference. So what's going on in that interaction right here in the middle? All right, definition first. Wave interference. All right, wave interference is the effects on the amplitude of a wave in a medium when another wave passes through that same location in the medium. All right, the effect is actually on the amplitude of the medium, not the amplitude of each wave. Each wave remains the same because the energy of the wave passes through. It doesn't bounce off, but it does have an effect on the medium, and it has an effect on the apparent amplitude that the medium is experiencing due to that energy moving through it. Okay? And so what that means is, what happens when two ocean waves move through the same point? Let's say it's, the opening on a seawall at a harbor, and you've got waves coming from one storm in the north and waves coming from another storm in the east, and they happen to meet right there at that time, and those waves are going to pass through for as long as those storms lasted, and they're going to create some sort of interesting interference at that opening. Let's say we have sound waves. You have one person saying one thing over here, you have another person saying something over here. Person down here is going to hear that person up there. They're also going to hear this person over here. And the interference at that location is going to be a combination of those two sound waves. All right? Light waves I just described with the billiard table reference. If at the instant of interference, at the instant when the waves start moving through each other, both waves have the same direction of amplitude. Same direction of amplitude. Then what we're going to get is a constructive interference moment. Right? So let's say that we have two waves here, a green wave going this way, a blue wave going this way. The green wave has a certain amplitude, and it's in the positive direction. The blue wave has a certain amplitude, and it's in the positive direction. When those two cross over in the medium, that crossover moment is called a superposition. And the amplitude of the superposition is going to be the vector sum of the two individual amplitudes. So since this is plus, you could call it plus 1, and this is plus 1, the amplitude over here would be plus 2. Let's say, for instance, that the blue one actually had an amplitude of plus 3, and this one was only plus 1. I would have to draw a bigger one here. Once you got here, the amplitude I would have to draw would be plus 4. The superposition amplitude would be plus 4. Now, that superposition only happens for an instant in time. Very short period of time, all depending on how fast the waves are moving. All right? And so after they interfere, boom, the green one goes on, the blue one goes on, and the medium goes back to being normal. Okay? But for that instant where they are actually passing through each other, we get this moment where the amplitude gets larger. We call it a superposition. We call it constructive interference. Okay, and we know that waves don't just always vibrate in one direction. If you're going up, the next part of the wave that's coming through is going down. If you've got a high pressure zone, the next part of the wave that's coming through would be a low pressure zone. Okay, so here we have an example where the pulse of the wave, we have a positive amplitude here, a negative amplitude here. The superposition is going to be the vector sum of those two. So the positive plus the negative levels the amplitude of the superposition out. All right? Now let's say that this one had a positive 3 for its amplitude, and this was a negative 1 for its amplitude. I would have to draw that bigger to indicate that. And then over here, the superposition would only be plus 2 because it's plus 3 plus a negative 1. So the superposition wouldn't lay flat, but it would be a lower hump than what we would see. If they're equal, here's the, if we were to see this motion actually occurring in slow motion, the green one would be coming along, it'd be moving along toward here, and then once it started encountering, right at that instant it started encountering the blue one, we would actually see it shrink down until, for an instant in time, the blue and the green cross over, and all we see is a flat line. And then we would see the green one start rising up from there. We would see the blue one start sinking down from there. And the blue one would continue on, and the green one would continue on. Okay? Destructive interference. Your amplitudes are in opposite direction. So the vector sum results in a smaller amplitude for that superposition. Okay? Now, what if the waves are continuous? What if the waves are moving through each other and the wave is coming and just keeping going and there's more waves behind it and it's all the same wave and everything, it's a green light going this way. Okay? And we've got yellow light coming this way. For this interference area that's going on, we would actually create a zone where the interference of the green light and the yellow light would create stationary locations of constructive interference and destructive interference. And to somebody standing outside that, we would notice that, oh, there's a bright spot there with the green and yellow light interfering together. Oh, right, kind of, sort of in between, we've got the green and the yellow light interfering, but it's destructive. And then just a little ways away, half wavelength of the way, believe it or not, it'd be constructive, and then destructive again, and then constructive, and then destructive again. But those places where the constructive interference and destructive interference are happening would not appear to move. They would be stationary. There would be a bright spot, a dim spot, a bright spot, a dim spot. If it were sound waves, let's say two instruments making identical notes, playing identical notes, to someone sitting over here, what they would hear is a loud tone that is those two notes. And then if the person moved just a little bit to the side, all of a sudden they would hear nothing. Constructive interference, where the notes interfered constructively, and then just a little ways away, half wavelength away, destructive interference. And for sound, destructive interference means you wouldn't hear anything if they both had the same volume. Move a little farther, constructive. Little. But notice the pattern isn't changing. And when that happens, we call this standing pattern, this stationary pattern of constructive and destructive interference places, we call that a standing wave. Okay, so standing wave. All right, standing wave represents a stationary pattern of constructive interference superpositions, which we call antinodes, and destructive interference superpositions, which we call nodes. All right, so let's say I have a wave on a string, and I'm shaking the string, and the string is attached over here onto the wall. Well, when that wave energy hits that point, it reflects it back and it reverses the amplitude. All right, that's an interesting phenomenon that takes place. And so with the reverse of the amplitude, if it was going down on the way in, it'd be coming back on the way out. All right, now, as that wave energy continues to go back and forth on itself, what we would see is it would create a pattern where at the wall, it wouldn't move. And yet the energy is still coming into it and reflecting off of it. And so this would be a destructive interference point. Destructive interference point. Destructive interference point. Notice that we get a constructive interference point, all right, a quarter of a wavelength away. Half wavelength from that, another constructive interference point. Half wavelength away, another constructive interference point. Constructive interference point. Constructive interference point. If it's constructive interference, we call them antinodes. And if they don't appear to move, it's a standing wave. All right. You can do this in your basement. All right. Take a spring, take an elastic cord, and you can start shaking it. And you can get it to just the right frequency for the length that you have and for the tension that you have on the string. You can get it to vibrate like this. You could get it to vibrate just, one time. It'd be a half wavelength mode of vibration. Okay. And so this standing wave pattern that's created, this standing wave pattern is the result of the constructive and destructive interference of the wave hitting and then getting reflected back on itself in the boundary. This can also happen with two waves just moving through space. The interference of those two waves, as long as the waves are continuous and continuously moving through the space, they will create an interference pattern that creates a stationary pattern of constructive and destructive locations, nodes, and antinodes. Okay? So, wave interference. Wave interference happens when waves are moving through the same medium at the same time. Okay? If the amplitudes have the same direction, we create a location, a superposition that is known as an antinode. And that's where the amplitudes will add together. And at that position, it will be the vector sum, the addition of the two of them together. Okay? If you have nodes in opposite direction passing through that superposition, then it's destructive interference. It creates a node, and the amplitude of that node will be the vector sum of the two amplitudes, but that vector sum actually creates a subtraction. And so very often you get a flattening, especially if the two amplitudes are identical in amount but opposite in direction, and you'll get a 0 point for your node. All right. Otherwise, you get just a decrease in the overall amplitude. Okay. Interference, waves passing through. Lightsabers wouldn't work. Sorry, George Lucas. Sorry. As much as I love Star Wars, that was one thing that even as a kid, I went, really cool? Wrong. Can't happen. Okay. Have a great one, folks. This is your friendly heavy physics teacher signing off once again. I don't know when I'm going to see you. Hopefully before the end of June. All right. I really hope we get through this quicker rather than longer. All right. Bye bye. Have a good one. Stay safe. Stay healthy.